I'm Tom Taylor. So I have the honor to, one of my mentors, and did my master's and PhD under Dr. Puppala. So I'm going to kind of read through a quick bio of his. It's for you young engineers out there that can read from the iPhone. This is what happens when you get older. You have to take it from the iPhone and put it in large print so you can read it. So let me go through his bio, and then I'm going to do a couple personal things for you. So Dr. Anand Puppala currently serves as the A.P. Wiley and Florence Chair of Zachary Civil and Environmental Engineering at Texas A&M University, as well as the Associate Director of the Center for Infrastructure Renewal. Both appointments started in September of 2019. Before that, he served as the Associate Dean of Research and Professor in Civil Engineering at the Department of the University of Texas at Arlington from 1996 to 2019. I took Dr. Puppala's first soil mechanics class in 1996. Dr. Puppala is currently the chair of the soil mechanics section for the TRB and is a member of the Design and Construction Group for TRB. He also served as the chair for the GI, Engineering, Geology, and Site Characterization Committee and the TRB Committee on Soil and Rock Instrumentation. He's a current member of the GI Technical Coordination Council. Dr. Puppala also serves as the president of the United States University Council on Geotechnical Education and Research from 2007 to 2009. Dr. Puppala has been conducting research on stabilization of expansive soils, sustainable utilization of recycled materials, dam safety and embankment slope stability, in situ intrusive methods of site characterization, infrastructure resilience, and pavement material characterization. Dr. Puppala has been the recipient of several research grants from both the federal, state, and local government agency. Dr. Puppala is the director of the NSS Industry University Cooperative Research Center on Composite Civil Structures at Texas A&M University. Dr. Puppala's research scholarly record includes over 450 publications and over 200 journals and geotechnical publications. He's edited 7 special publications. Dr. Puppala is a current editor and member for several major journals, civil engineering, including the ASCE Journal of Geotechnical and Geo-Environmental Engineering. He has given more than 50 keynote lectures and several invited lectures at various parts of the world. He supervised 35 doctoral and 52 master's thesis students and is currently advising 10 doctoral students and 3 postdoc students. I started in 1996 with him. I started a business about the same time, and one of the things about Dr. Puppala, he's really interested in engineers growing their knowledge base. He would always talk to me, I would tell people, I really want to go and get my master's and my doctorate. And they're like, you own a business that's successful, why do you want to go get a doctorate and a master's? Well, when I talked to Dr. Puppala, he said just the opposite. You own your own business. You really need to get a master's and a doctorate. So he's always been extremely helpful to the students. A lot of his students are here. One thing that he's always made sure that the students that he has under his supervision always come to these types of conferences. So if you haven't met him, I highly suggest you meet him. He's been my mentor, my advisor, my colleague, and my friend. With that, I'd like to introduce Dr. Anand Puppala.
Mark Rubio movement. I need water here. Thanks, Tom. It actually took a lot more than just talking with him. I had to talk to his wife also to convince him to come for a PhD program. It's really, I know it's a big commitment because he's so busy person, but believe me, he has done a superb job with his research. We are actually 2 papers right now working on it, and I hope to submit them soon if his family permits it, right? So, all right, this is a really, again, a great honor to be given this lecture. And I know my good friend, Professor Briard, said, Anand, some good news is coming, but I can't tell you. I was thinking some proposal getting funded or something, I thought. The next day evening, I got the email from ASCE. It is really humbling, and I'm really honored to get this invitation. Again, the topic is over there. You can see here, case studies on problematic soils, characterization challenges, solutions, and novel monitoring methods. Again, as Tom said, I was a faculty until September at UT Arlington. I recently moved to TAMU. You will see why I had to go there, because the best in expansive soil sitting here are all over there, so I can do more work over there. With that, let me show you some pictures of my collaboration in the past with Professor Peck. These are some of the pictures taken. First one is 2000. As a faculty, I was taking a foundation training class. It's the ADSC training class. I was at the Denver airport outside. There's a bus that goes to Fort Collins. I was sitting there. In the very front row, Professor Peck was sitting. So I was the second one in the bus. So I just went to the front, and boy, I had a wonderful conversation with him, 40 minutes. And he was telling me how he spent his childhood in New Mexico, working as a student internship, and all the things. In fact, his dad designed one of the bridges, which I happened to visit a few days back near the Denver. So it was a big honor. And again, you see the second picture is on the right side. Suzanne, I don't know if she's here somewhere, but I'm pretty sure yesterday evening we were talking. And again, my students want to take a picture. So that was in Denver, Geo-Congress. The common thing is, look at the picture in which his face is so happy, like he's a great mentor. That's what you get with Professor Peck. He's really he wants to encourage it, always big smile, broad smile, and I think that's what we need. And I got so encouraged and, a lot of enthusiasm whenever we see him. And the big thing is really this conference. This was the first International Soil Mechanics Conference in Istanbul. I was assistant professor, got an NSF fellowship to go travel there. And what you see is the Terjagi tour. Terjagi spent some time in Istanbul. So these are the 4 spots we are traveling. And the tickets were sold out. I didn't have tickets. But I was standing at the registration desk, and somebody left 2 tickets and said, hey, I can't make it. Anyone want to take it, take it. I happened to be the first one to see them, and I grabbed those 2 tickets. I went the tour with Professor Peck and a lot of people, like 70 people. And the picture we took is at the Roberts College, where Terjagi has a memorial set up there. So he took probably 70, 80 pictures with everyone in that group. Everyone wanted to take a picture with him. Happened to take one with the Professor Mesri and Professor Peck. That was, again, I was so lucky to get those tickets. So now I'm coming to my talk. Again, my talk is going to have 5 major talks. The first one is Introduction to Problematic Soils. As I mentioned, I live on expansive soil. My home is on expansive soil. Just like our previous speaker said, they're close to earthquake. I am sitting right on top of expansive soils. In fact, I do sometimes go around my home to see if there's any cracks developed. So that's one thing, it's a kind of humbling experience, but something that's very important. And then man-made soils, which is, again, is a different type of expansive soil. It's not natural soil. You'll see a little bit more about them. And then I'll talk about characterization challenges. We did make some advances in how we characterize expansive soil. More needed, because we still rely, some of the designs, we rely on the plasticity properties, which are very basic in nature. You'll see what I'm talking about later in the case studies. And I have 3 case studies. Each of them is going to deal with expansive soil. And then I will go in the end a little bit more, because one of the things as a faculty member, I always have to look for new opportunities where the funding is. And we're doing quite a bit of work with the visualization now. And I hope some young faculty here, I would like to convince them, maybe you may want to start some of the research that I'll be discussing in that section. And I have one slide that talks about summary. So this is the quote. The quote says, in soil mechanics, no evidence can be considered reasonably adequate until there is sufficient field experience to determine whether the phenomena you observe in the lab are indeed the same as those in the field. Basically, you have to mimic what happens in the field in the lab, and that's the most important thing. Again, Professor Peck, as you all know, this is where case studies play a major role. So with that, let me start with expansive soil. And these are billions of dollars of damage, annually. It's not just I'm talking about like several years. It's actually every year we have so much damage. Comes from pavements, dams, embankments. And homes is a big failure, I mean, a big major issue. I'm not actually exaggerating, but in Dallas, we used to have 50 to 60 foundation repair companies just in Dallas City. Unfortunate thing is every few years they change their names. They bankrupt, they get a new name. But that said, again, this is a big issue. Every 1 in 2, in some subdivisions, in some cases, 100% homes have issues with the damages. And that's a big, expensive thing because you have to spend a lot of money to repair them. And most expensive soils are monazite or smectite clays. Again, I mentioned the design is basically based on the plasticity index-based characterization. We do use suction, we do use swelling testing, but again, it's not always very common. I was hoping more, the less focus right now, but my research is more focusing on clay mineralogy. So you're going into soil chemistry. Again, the one that's very important is monazite mineral, which is smectite group. You see the specific surface area, how big it is. A few grams can spread whole football field. And this you'll get from Mitchell and Soga book, which is very true with this material. So anytime you have a monazite mineral in your soils, you are talking about some extreme problems, and high cation exchange capacity also. So these are some pictures. Again, this is my PhD student from Thailand. He was, this road is few months old. It is Paris district, which is like an hour-and-a-half drive from Dallas. The crack we are measuring there is almost like 2 feet he was able to push. I'm pretty sure it went much deeper. This time when we took this reading, we have almost 2 months of drought. There's not much rain. So the cracks developed on the side of the pavements, went into the paved lanes, like this lane you see. This is a part of the one side of the lane. And again, they had to repair within few months the whole pavement because you have so much of heaving on this road, and this is a big failure. The other thing you see is this one is their residential home failures is very common in our area, including this one. And we also have a lot of embankments that fail because of the swelling soils we have in them, And then a lot of times we get roller coaster rides on the pavements in our region. So a lot of times they want to know, hey, sometimes they ask me, Anand, do you think I should buy a home in this region? I say most engineers can address your problem, but better to drive around to see what type of roads you have, then you get an idea whether it's a bad area or not. If you do have bad area, you don't stop buying there. You can still come up with a better foundation. You can come up with it. And in fact, that's what I did in my foundation for my home. I was able to increase a little bit more by doing some testing in my lab. So I'm very proud of that. And this is very common also. We have a lot of problems where we have MSC walls, because a lot of times MSC wall behind the walls, we have backfill that are expansive in nature. Traditional design for walls, we don't include swelling pressures. We only include Rankine's pressures. So you add a swell pressure, you will see the lateral spreading or lateral movement is going to be more. And you have a lot of times, wall starts moving away from its place. And one year, we have wall on I-30 near Dallas. It moved few inches, and Barry Christ was involved in the design, in the investigation. And that lane was closed almost for 4 months and was a tremendous problem because it caused a lot of traffic delays for morning commuters to going to Dallas. So again, this is coming because of your soil behind there is where it's causing swelling and it causes the movements. And this is one of the things I'm going to talk a little bit is embankment failures or slope failures. So this is one of the dams you can see on both sides. So if you have extreme drying, the first rain or second rain, you have a lot of what we call is the skin slides or shallow slope failures. And each slide, it costs sometimes 50 to 100K to repair them. Unfortunately, the repairs are very simple. They just push the soil back and compact it and leave it. And then 2-3 years again, you will have that another skin slide. So it's not a very good permanent solution. So we did some research with the Army Corps to address this problem. So the one you see on the right-hand side is the Joe Lake. So that crest completely collapsed several years back because we have cracking. The cracking went all the way to the crest, and it caused the failure of the road that is on the top of the crest of the dam. And then there's another type of expansive soil. This soil is actually first time this problem was mentioned by Professor Mitchell in his Peck lecture, and also in his Tajagi lecture, he was talking about the parking lots in Kansas having this heaving. And then subsequently, a lot of other folks actually have done, Hunter, Little, and several others. So basically, this one came from sulfates. So if you happen to have any of these sulfates in your ground, and you stabilize them with cementitious materials like lime, cement, You're actually, instead of making them expansive, or I mean, less expansive or more strong, you're actually making it worse, because you will see later, these minerals will react with your soils and form a compound called ettringite, and that ettringite is very, very expansive mineral. It can lift your even concrete pavements badly. So you can see the picture here. So this is gypsum. I have a lot of nice gypsum deposits in my office. So if you put it against sunshine, you'll see they're like almost sparkle. So this is one way of knowing you have a gypsum or not in your soils. I recently gave a talk in Paraguay. In some part of the Paraguay has a lot of these gypsum soils. So the roads built on there is having huge amounts of heaving problem. So some of our research in Texas is actually addressing this issue. Again, this is not just confined to in U.S. It's a worldwide problem. You can see gypsy soils all over the major continents. You have this problem. So, later I will show you more. But this is some of the pictures of this, sulfate heaving, what we call. So you can see here in this picture. This is just during the curing process. There is a small, heaves that happened right after like a few days, like in this case 3 days. So the heaves actually is your sulfate heave. And then they go back and rework it, but again, it can restart it. And this particular one is a Joe Pool Lake Road. Again, this road is Army Corps road. It's not a very thick road, but this, within 6 months, this was damaged. They had to spend $400,000 to repair this road. And this is not just roads, even runways, we have this issue. So this is DFW Airport taxiway. So the taxiway, we have a lot of cracks here. This is a lot of differential heaving, all happened because of sulfate soil. So again, this is another major expansive soil, but this I call man-made because it came from your stabilization of the soils with the cement or lime products. So I will talk about characterization challenges with expansive soil. And Professor Briaz has done tremendous amount of work on this thing, and actually we are working with them on a report. So a lot of times when you look at how we design the soils, we look at the PI. We do swelling tests, we do some suction tests indirectly, but majority of the books that we look for stabilization design, it actually looks at the PI. So I'm showing you two soils here. You can see Bryan and Fort Worth. They have different numbers, but if you look at the PI, they are almost close to each other. Same thing, two soils here. So this soil source came from different districts in Texas. So again, Bryan district, Fort Worth district. So again, later you will see these are not the same soils. They're different. So that's something, based on clay mineralogy, I can tell. But if I just do plasticity index, I completely miss this picture. So that's where I think, it's important to show that we really have to improve our soil characterization. So this is the second topic of my focus. So I'm going to go here. So one of the things we did is we have a 3-year NSF study, and a couple of students here, Bhaskar Chituri and Arvind, they all did this work. So part of the work was done with, again, Arizona State University, my good friend Claudia Zapata. So we have a collaborative project. So what we did is we have taken several soils, and we looked at their clay mineralogy, and then you'll see how we did that. Then we also did mercury intrusion porosimetry. And then we did on-site testing on soil water characteristic curve, which is important. You will know how the moisture is propagating or flowing through your soil. And then we did the macro testing of swell properties. Again, there's a lot of fundamentals involved here. We are looking at the micro level, porosity, and how the clay mineralogy, how they all interact with water, and how it causes your swelling. So this is the thing. One of the things that came up is we came up with some models. Again, this is more intensive work because you have to include some additional testing. But in my opinion, this will help. Unfortunately, most of the time when we have a failure, we do the forensically, we do all these things. We don't do at the time of beginning of the design. Okay. So here is all the properties that are accounted, both on composition side and environmental side. So if you look at your soil specimen here, you have void distribution, and then you have soil fraction. You have non-clay, which is sand and silt, and then you have clay fraction. You have a lot of other minerals, but I'm only listing the dominant minerals, montamonite, illite, and kaolinite. As you know, this montamonite is a highly swelling. This is low swelling, so you have different swelling index. So if your soil is rich with montamonite, obviously you can expect swelling. But if it is rich with illite or kaolinite, moderate swelling. But mostly kaolinite, predominantly, you do not have a major issue. It won't be a swelling mineral, swelling soil. So The one thing we did is with Bhaskar, he's now at Boise State, is we looked at this mineralogy. And this came from Mitchell and Soga's book. So they have identified the range of properties. So you can see all the cation exchange capacity, specific surface area, and potassium. One thing I want to mention here, the potassium main source is, again, for illite, comes from potassium. And that's what we thought. But believe it or not, there's another type of feldspar, which is potassium feldspar, that can contribute to kaolinite. So we had to make some correction later. So initially, everything we thought potassium is going to lead to illite mineral, but there is some part of potassium. This is from my geology friends. I learned it can actually come to your kaolinite also. But it's a very small amount, and very few places have this potassium feldspar. Unfortunately, Dallas geological formations have potassium feldspar. So I had to go back and make those corrections. So basically, the equations are straightforward. So you measure these three properties, CEC, SSA, and total potassium. And again, we have published quite a bit on this. If you are interested also, please send me an email. I'll be happy to share these procedures. So then you solve these three unknowns, because the unknowns are kaolinite, illite, montmorillonite, and then you get the three unknowns can be solved. But if you look at it here, there's a range. So you do not know which ones you are. So we developed an optimization Microsoft solver program. So that solver program can feed your measurement data, and it will provide you approximate mineralogy. I said approximate because we did not include other minerals that are present in the soils, because you have, you may have halosite, you may have other types of chlorite. So we are not including every mineral, but we thought these are the three ones we are interested. So once we developed the procedure, we validated with some well-published research, and actually it came very close agreement. I'm not going to say 100% agreement, which we never get in geotech. We got almost 70 to 80% of our validation study showed a good agreement with our equations using these three properties. So we have a way to measure it. There's other ways you can do. You can do extra diffraction Rietveld analysis. There are several folks use that. Again, in my opinion, this measuring chemically, chemical characteristics are a little bit more rigorous, but it's much more also provides you reliable information. So some of the models we did is like one of the models I'm showing you here. So what we did is we looked at our clay mineralogy, or chemical mineralogy fraction. So what you see there is the equation. This is the only few equations you'll see. You won't see that many equations, but basically, we looked at the clay fraction here. So this is our swelling factor. As I said, most of the swelling comes from montmorillonite. That's a 90. Illite is 9, kaolinite is 1. So if you take 100, we normalized it 99 to 1. Okay? So basically, if you have high montmorillonite, SF swell factor is high. So that's our parameter for what we call is a chemical parameter. The second parameter we included is, again, mechanical hydroparameter. We do SWCC, soil water characteristics curves. So, and also we have the void change during the process. So we used a slope of this curve that gives you the mechanical hydroparameter. So we came up with these factors are not, separate. They should be inclusive. That's why we used a pi formula. So this is our equations for them. So what you see on this x-axis is the parameter we measured on 8 soils taken from all over the U.S., different locations, San Diego, Denver, every other place where we know an expansive soil. So we collected them and studied them in this research. The x-axis is this parameter, y-axis is our swell test. There's a decent correlation. With more data, I can hopefully improve this correlation. But basically, we felt, by including, clay mineralogy internally and also the pore distribution and also water retention properties, you can improve your characterization of them. And then I go to another model. This is the one which is we use mercury intrusion porosity. So we inject our mercury at different pressures, so we can measure micropores, mesopores, macropores. And that's important because your soil, which is predominantly clay, the water moves through these pores. So you need to know which size of pores you have. So one thing we did here is once we characterized them, all the samples at two different density conditions, we measured something called, here is our, the ratio called TSAR. This is called total surface ratio, area ratio. So the way it works is, here is your soil, you have a lot of minerals inside, and then you have a lot of pores. So the water has to go through your pores, assuming they're connected or saturated, and then it should be touching your clay minerals. So first thing is, from a clay mineralogy, I showed you a method. We are able to identify how much % of each mineral we have. So we went back and calculated how much surface area of whole clay fraction we have, and we are mostly interested in monazite. Then next thing we did is using this MIP. We looked at the pore, and that is where it's going to be filled with water. So we come up with a ratio. That is the ratio. So if you have more interest on this paper, please look at the engineering geology. It's published. ASCE JGG also published this paper. So in both cases, again, you can see the correlation. So this is the x-axis is that ratio. Y-axis is our macro parameters, measured parameters, decent correlation. Again, we can develop some robust correlations that can give us better idea of swell characterization. So if you look at it, obviously we are asking more from your testing. You need a mercury intrusion porosity. Where do we have that? We don't get access to every place. A lot of places, mostly universities, have this research access. But one thing I can mention, there is the real practice integration will take time, because obviously I expect this to be a little bit time. But if you look at your quote from Professor Peck, research, whatever we develop, they need to be simplified and develop procedures so that the engineers, can use it with a more, easy way instead of doing it with all the testing. So for that, a little bit of empiricism is needed. So we need more database, and hopefully more testing on this. We can come up with a way to correlate these properties. Will definitely help with our practicing profession. What I'm hoping is we can come up with the better models that can improve our characterization. So right now, unfortunately, we only do whenever we have a failure. Okay, if there's a road that failed, we get the sample. I was always asked to find the clay mineralogy, but I'm hoping we will do more before we design that road or we design the dam. We can characterize them. So that's where I think, with time, hopefully with more database, we can develop equations that can be, simply used in the practice with a little bit more testing data. So I want to go to the case studies. So before I do the case studies, I would just want to give the quote again. The most fruitful research grows out of practical problems. Again, don't have to mention so many of our works are well, defined by the practical problems. Every one of our research is leading to some solutions that improve our sustainability, our resiliency of our infrastructure. So, in our expansive soils, in my opinion, we are working a lot, and Professor Briard, Professor Litton, Professor Little, Sandy Houston, Bill Houston, several folks, Professor Ray, all those folks, their works are pretty much going towards practice. So there are a lot of things that we do actually lead to some implementable research. So I want to show you some 3 case studies where we have included 2 on pavements, 1 on slopes, all of them dealing with expansive soils. So I'm going to start with my first case study here. So my first case study is, again, expansive soils, as I mentioned. And typical practice is mostly use chemical stabilization. So this is a typical lime and cement is very common. Lime is probably 70 to 80% of the market for stabilizing expansive soil. Cement also, you definitely see them used also. In some cases, cement actually provides you better strength properties. So again, this is quite an interesting practice. And then you also see recently a lot of interest on geosynthetics. There's some types of geotextiles that are used. We are looking at one of the geotextiles to remove the moisture from the subsoil so we don't have the heaving. So again, there are a lot of interesting ways to stabilize it. So the one I really focus is here on chemical stabilization. So for this project, it's actually funded by Texas Department of Transportation. It's a joint project with UT El Paso, with Sohail and our team. And again, we do, all you see on the soil type, different nice cities, those are our districts where we got the soil samples. So if you look at it, each soil we characterized with our methodology we developed. So there are 4 of them in red font. All these 4 have a high monazite. And this is very important. Later you'll see. And please remember, if you are, I think Bob just left, but if you're living in Austin, definitely you're sitting on an expansive soil. You're living in Fort Worth, which me and Tom, we live there. We have expansive soil. Paris district, which I showed you the road, that has the cracking. Within the same district, you have soils that are non-expansive to expansive. So that's an important identification. So one of the things we did is, if you went with the design, so that's going to be really opens up your eyes. So if you recall, I showed you this slide where we have same PI, these 2 soils, 3129. Now look at the dominant mineral. Brian, where I am now, we have a better soil. We have a kaolinite-rich soils. Again, you may find some areas where this may not be valid. Again, we did only few studies, right? But again, Fort Worth, we definitely have a lot of pavement issues. So monto-monolite mineral is very dominant. And the second one, again, is Paris, 36, 37. But if you look at liquidity limit or even do liquidity index, it will be better than just relying on PI. So this explains why we should go a little bit away from PI, based design. So this is the PI-based design. So a lot of times the stabilization guidelines, this is one of highway agency design. They look at your PI number, they come up with recommended things. So anytime you're talking about 15 to above 35, lime is very common. So most times you see lime is recommended for this. But again, when you go to PI more than 35, you are talking about soils that have a high monto-monolite. So you really have to look at it a little bit differently. So what we did is on all the 8 soils I showed you, we did come up with a lime stabilization design from Eads and Grimm method, which is called pH-based method. So each of them we came up with 6 to 8%, except for one district, FAR. In FAR district, only uses 3 to 4%. That is the district practice. So we had to, as a part of the textile, we only did 3 to 4% for this project. So let me show you some results. So we did the stabilization design. We mixed with soils with the chemical, and then we did all the swelling and everything. At the beginning of the design, it worked very nicely. But when the roads are built, they are in the field. They have exposed to the seasonal changes. So you really have to do a durability test. You have to do the mostly wetting and drying. If you are in Minnesota, you have to do freezing and thawing. But now you have a small area. You may have to do all 4. North Texas is fitting into that area. We have a lot of cold seasons. So we have to come up with a more new procedure that has wetting, drying, freezing, and thawing. And I don't know if that may be the worst case scenario that may lead to, because sometimes we see after freezing, we have a lot of road issues. So in this case, it's wetting and drying. This is the ASTM procedure. So 5 hours wetting, 42 hours of drying. So typically, you're talking about close to 2 days of testing. So in each of this case, we tested them several cycles, and we target is 21 cycles of wetting and drying, and see if the sample is staying, how much volume change is taking place. So every time we do wetting and drying, we were looking at the volume change. Plus, we also took some samples after certain cycles, and we tested them for unconfined compression strength. Because most of the stabilization design relies on the UCS. So we want to see if after wetting and drying, the UCS staying same or is it going down. You will see some interesting results now. So the first one here is the Fort Worth clay. So if you see on the top, untreated, within 1 cycle, the sample collapsed. Obviously, no treatment, nothing holding it, so we have an immediate failure. The second one is your after you did it with the lime treatment, 6% lime, it did well up to 10 cycles. After 10th cycle, it failed. So you may get a good performance for a few months to a year, or maybe a couple of years, then you may have an issue. So that tells you why we have, in some roads have problems in year 3 or year 4. This explains it's a sub-process. It's not like an immediate, or it's not like a 10 years or 20 years. Some of these mechanisms of swelling and shrinking will have a bad effect, but it takes some time sometimes. So now show you the results. So if you look at here in this picture, we did the plot here on the strength. So we started with the no cycles. This is the wetting and drying cycles. You can see this soil is a Keller soil, is a kaolinite. We have slight loss, but it's not very high. And look at the volume change. This volume change is below plus or minus 5%. And this is okay, because a lot of our monto-monolite soils go up to 10%, even higher. So in this case, we have actually all 21 cycles were completed without any problem. It's because it's a kaolinite soil. Let me show you another soil. This is the monto-monolite soil from Austin. You can see the strength, how it everything is this is the untreated soil, and then this is a cement-treated soil. So lime-treated soil failed after 12 cycles, and then volume change you can see here is actually going up. And again, this is something we saw. This material maybe with cement we may get a little bit longer life than lime, but nevertheless, this being a monto-monolite soil, using 6% lime is not sufficient. You may want to go much higher than that lime stabilization. And a lot of current practices use between 6 to 8%. But that explains why a lot of times we have issues within a few years after surveys. Again, we used this information, and then we came up with this table of all 8 soils. So I want to mention on the top, all these 4 soils that has monto-monolite mineral. If you look at it, we never completed 21 cycle. Everything that failed 12 cycles or less. And then you look at the strength, 0% strength. So we never were able to complete the testing. Samples failed before the full durability cycles. So it's all because of the mole-to-mole line. And there are the 3 other soils actually worked well, these 3, except for B. In this case, I mentioned they put very low lime. That district practices use lower number. We feel it requires much more than maybe 6% would have helped it, but they did not give us full life. But basically here, anytime you have a kaolinite-rich soil, even though you may have same PI, that soil is okay. It will provide a good resilient foundation support for your pavement. But if it's a high mole-to-mole, you will have an issue. So this gives me a lot of times, sometimes you sitting in a meeting where some districts say, we never have a problem, but other districts say, no, we have a problem. I mean, the reason is we are talking about apples and oranges. We're not talking about same soils. That's because their characteristics are different. PIs may look same, but they're not. They really, you have to look at the clay mineralogy. So one of the things we did is we came up with this modification in our design practice. So one thing we did is look at the mole-to-mole, and then if you have mole-to-mole, you need to redesign. Not only design with the higher stabilization, you may have to continue doing durability cycle. In some cases, we went up to 10%. Again, not a sustainable design because you're putting more cement or lime into the soil, but sometimes it's necessary because that structure is going to fail. Okay, so this is one of our first case study. My second case study is on ettringite soils, which I call sulfate-rich soils. So this is where I think, as I mentioned, Professor Mitchell. And then later, Dale Hunter, he did a wonderful work, a dissertation work on this material. It's in Las Vegas. This is also published in ASCE Journal of Geotech. So what they did is they looked at a road built on Las Vegas. That road is actually lifted by almost, believe it or not, 24 inches. Please look at the JGGE paper. You'll see how much heaving just came from this soil that is treated with lime. All because of the gypsum and lime and reacted and formed a mineral called ettringite. This is the ettringite structure. Ettringite, chemically, did I say no more equations? But I think a few more equations, chemistry equations, okay? So, but it's a very simple equations. So what happens is why this problem starts. The problem starts from this. Anytime you design a chemical stabilization, you are increasing your pH. So at a high pH, your soil starts releasing your alumina or silica. A lot of times, these will form with your chemical additives and form pozzolanic compounds. In this particular case, what happens is this. You have alumina that comes out here, and then again, you have this alumina that comes out here starts reacting with cement or lime calcium component, and then it also reacts with the sulfate. This is the sulfate source. And all these things, under the presence of water, gives this compound, ettringite. This is ettringite. Ettringite is highly swelling mineral. It can cause huge amounts of heaving. In the past, before Mitchell's lecture or even before that, they used to think it's coming from underlying subsoil, but it's coming from your own stabilization, right underneath your highway pavement. So this is a major issue. So now if you look at our current practice in geotechnical practice in many southern states or southwestern, they include sulfate as a part of geotechnical characterization. The problem is this. Sulfates they travel with groundwater, and their pockets, they are not uniform. So if I can easily miss, if I do like few tests at 3 or 4 spots, I will easily miss the sulfate characterization. So you need more testing for sulfates. Fortunately, we have some simple electrical conductivity methods that will give you preliminary screening. Yeah, this seems like a sulfate. We can do more chemical gravimetric methods to confirm it. So you can do it, and that's one of the practice in Texas. They actually have a method that's 1 or 2 hours. You can get some numbers, preliminary numbers, and then you can do 24-hour test to confirm that. Again, sulfates heaving is a major issue. So these are some of the studies we documented over the years. There are more, but I'm just showing you one slide here. One thing I can tell you, in all these areas, if you look at there, the lime and cement caused the thing, and then the important thing is here, this sulfate numbers. Some folks said 3,000. But I have seen soils with 1,500 parts per million has a heaving problem. So it's very difficult to identify. It all depends on your compaction conditions. If you compact high density, your void space is small. Then if ettringite forms in that void space, you can see the heaving effect at the surface very quickly. So it's all actually, depending on compaction conditions. So a lot of times I get to ask, hey, Dr. Puppala, can you give me a sulfate number at which I am, I said, if I say something, the egg falls on my head, because if I say 3,000, I have seen soil that has 1,500 has a heaving that is close to 8 to 10% in the 1D swell testing. So I'm very careful. I will never say, don't just say the number, just try to do some testing, and then you can confirm it. So the two things we did in our research in the last 12 or 14 years at UTA, we have done two types of tests. I want to quickly mention here. These are ones I call less than 8,000 parts per million. This is some of the things. I won't vouch this because I said, even 1,500 may have an issue. But we looked at several additives. And again, GGBFS is being used even in UK very successfully. And also type 5 cement. We actually have successful application in real field. We're also looking at class F, because class F is low calcium. So anytime you put low calcium, it actually improves it. So we came up with the different things that worked for them. And again, a lot of these studies are actually, I have an NSF study, Army Corps, NCHRP, and then the US devotee funded study. We finished them. They're all related to this. But there are soils that have sulfates more than 8,000, and we have lots of them. So how do we stabilize them? Do we completely remove that soil and then redesign it? So we have a study from highwaytex.research. We looked at them, and again, these are 6 different soils from different regions in our Texas. Again, all of them here. There are a few that has already what we are looking for, but there's the one that are not. What we did is we spiked the gypsum. We added gypsum to create more than 8,000. So basically, we manufactured some, but we also used some natural. There are 2 soils I want to mention, Austin and Childress. They have very high amounts of sulfate. So one thing we did is we came up with, again, traditional stabilization design, and then we wanted to use something called mellowing. Mellowing is typically anytime you do a chemical treatment, you let it soak for a few hours and then go back and rework the soil. So a lot of initial, cation exchange capacity reactions can happen very quickly that can make the soils kind of non-plastic. That actually helps when you compact them. You may have a little bit higher water ratio, so you won't see the, the sulfate heaving in those soils. So we wanted to see if I use 3 days of mellowing, 7 days of mellowing, whether that will provide me a better stabilization of these sulfate soils. So we tried different mellowing periods here, 0, 3, and 7. 0 is what typically. But again, when you increase this mellowing, contractors do not like it. They want to finish the stabilization quickly. But in this case, if you do it quickly, you may have a problem where you have to come back and repair it completely. So it's something you have to probably wait. So there's some interesting results I want to show you here. So 3 of them. So the Sherman soil has this 24 riverside. These 2, if you look at here, the blue is your untreated soil. Then you have 3 different mellowing I mentioned. These are the soils. So anytime this final value at 3 or 7 is below this value, that means we effectively stabilized it. So we were able to do with mellowing 3 and 7 days. It worked for this soil. It worked for this one. But when we went to Childress soil, it did not work. Actually started going up again. So that soil has very high sulfate. So there is a threshold sulfate level at which we cannot use even mellowing. So we went back and did some more investigation. So we found out of 6 soils, 4 soils worked very nicely in our mellowing. 2 of them did not work. These 2, again, are Austin and Childress soils. Again, Austin has a lot of high sulfate soil. And when we did some more investigations, micro-investigations here, so we measured alumina silica. Unfortunately, these 2 soils have a low alumina silica. We need them. We need them for pozzolanic reactions. You need calcium silicate hydrate, calcium alumina hydrate. So when you have these 2 compared to these, it did not help us. So we need pozzolanic reactions to counter sulfate heaving. Unfortunately, we didn't get it. On the other hand, if you look at the voids, these 2 soils after treatment, you have the lowest amount of voids here. So compared to other 4, you need a little bit more void space. So sometimes we actually ask them to compact at the low densities that give you more void ratio. That void ratio is for space. So the yttringite is like a crystals that starts growing with time. They will hit the soil particles in the void, and then you will feel it at the surface very quickly. So again, we explained why it did not work. We feel anytime above 30,000 high sulfates, there should be probably look for a non-other way like a geosynthetics and other things. I don't think even mellowing works well for those soils. So we went, one of the things Professor Peck is always is check the validation. This we did in the lab. So we have a test site in the field. Again, this is the Paris district because, as I mentioned, they have very proactive research folks. They actually give us test sections. Again, this is our test sections. We did both with a different mellowing as well as fly ash. So constructed our test sections. Again, they nicely put our test sections where we had to go and collect the data. So it's done with a different mellowing. So I'm just going to show you this slide here. So 2 years back, our research project was selected by Highway Agency to showcase at ASTO. ASTO showcases this research that is the most implementable or practical research so that it will have a wider dissemination. So at the TRB, we did the ASTO rack. So at the material section, you choose our project to show. This is our poster. Again, we showed what worked for us, and we did clearly say that after 30,000, we did not find any other method right now that is effective. But that may be other materials that may work, including nano-silica or pozzolanic, other types of compounds which you very fine may work, but we haven't investigated them yet. So hopefully more will come. So I'm going to move to embankments, dams, and slopes. That committee, EDS, Tim Stark is somewhere over here. So that's his committee that nominated me for this, so I want to try to please them. So this is my case study on embankments and dams and slopes. Again, this is some of the, you may have a better video, but basically, we have a lot of embankments that are made of expansive soils. Again, you have sun. You always have cracks develop superficially. You will see some cracks later. And then the rain. Again, this is a poor simulation, a long time back simulation. And then the water goes in. Then you have soils that move in. Then the next thing that happens is we have a lot of skin slides like this. These are, lots of skin slides we have in our region. So this is the Army Corps project. They funded 5-year project for us to try different techniques. So you can see there are 2 dams. Both of them are very close to my campus at UT Arlington at that time. Grapevine Dam and then Joe Pool Lake Dam. They both have huge amounts of these superficial slides. So we studied different methods here. So here is the 4 different methods, including control. We have studied compost. Compost is biosolids. Why did we study compost? Compost is hydrophilic. So we thought being close to surface, they may absorb some moisture. If you increase 1 to 2% of moisture in your near surface, that will cut down your cracking. So that was our goal. Did not perform well, but that's a different story. But then we also studied lime with different fibers. So in each case, we instrumented. We have all kinds of inclometers placed, moisture probes placed. So, the 2 areas where we have cracks, you can see the cracks. As I mentioned here, this is the huge amounts of cracking on these dams on both sides. So we have cracks on control and compost. We did not have cracks on our treated soil section, which we expect them because the lime treatment increases your shrinkage crack resistance. So fibers actually add more tensile. So one of the issues when we did this project, how effectively we can mix fiber with lime in the field. Because fibers are discrete fibers. How can we mix it? Can they blow away from the wind? So we tried to do this. We were able to do everything at the toe of the dam and then move the soil back and then compacted them to the specifications. So these 3 sections in our study really worked very well. So we also did a lot of other things, including some slope stability analysis. So if you look at it using our, we did all kinds of shear strength, residual, fully softened, everything. I'm just showing you one property factor of safety is, less than 1 or untreated. Again, when you do lime treated, it does have an increase in strength. The shallow failures requires you to get some cohesion close to surface because you need some shear strength and you have to have some C prime. And phi prime is, is not going to be that effective because your sigma prime is very low. So anytime you add a lime treatment, if you can still keep that cohesion at what we call the drain cohesion parameter, small amount, that will increase your resistance tremendously, and you will not have a failure there. So you can tell why we can improve by using lime treatment in this case. It worked very well, including some inclometer readings we did. A control section has large movements at the surface. The treated soil worked very nicely. Again, this is the Army Corps actually released a R&D research report they call Data Safety Fact Sheet. So several other folks actually used this technology now to stabilize it. And very recently, we applied this technique of stabilizing with lime for a highway slope, which I'll show you quickly. So I'm looking at my time. So Again, this is performance indicators. The three top ones, again, the lime, where the lime is the important part of it, that is really a chemical treatment. So basically, expansive soil, if you want to cut down the cracking, you definitely need to chemically alter its properties. So we did an embankment, as I mentioned here. This is a big embankment slope along US 75. Again, this failure is if you see this picture here, December 2017, they had to shut down this road. So this is a 75. So this is December 2017, and then you see this failure in 2018. It took away a whole area, whole section. Now this failure went on the other side also. So we came up with a laboratory design for them. This is an interagency project we have done. So it's a 35 feet height embankment, 3-to-1 slope. You can see the swell properties pretty high, so it should shrink swell soil. So one of the things we did is we need to really alter the properties. So during the site investigation, we looked at it right next to this highway that failed. Let me go back here. Right next to the highway where we have, there's a farmland here. There's a lot of watering of the plants that is coming directly here because there's a cut section, there's a road here. So we see a lot of water that's coming out, so we thought we need to really take the moisture out. So again, we looked at all these parameters and we felt like, anything that comes from this farmland water, we need to see how we can drain them up. So our design is just finished it, and now they're finished the construction also. So when we did the slope stability checks again, untreated soil without any lime, we get 1.06. And after the lime treatment, we did the design again. You can see the stepped section. The reason why we did stepped is you don't want to put two different materials. One is a lime treated, the other one natural soil. There may be a kind of a slippery slope that may happen. So we did the stepped type of construction. It actually, just now, very recently, they finished a major part of it. It's still a few more weeks left to finish the project. Then we are instrumenting and monitoring. And again, Barak is instrumental in this project, one of my PhD student. Again, we felt like this design is going to give them better life. So we did mention about the drainage. So one of the things I can say is the drainage is taken out here. So this is the construction. These are the last month's pictures. It's ongoing right now. The important thing, as I said, is the benching. It worked very well. One reason why we had to take more time is other side of the road also failed. So the whole agency was repairing using our procedure. So our part of this whole thing is design, come up with the options, then also some drawing, and then instrumentation and monitoring. So I have at least 1 year left, but I hope I'll get another year of monitoring because we are a little bit delayed on this construction. And again, this is, to me, I think, I hope it'll work very well for highway embankment also. So I want to mention a little bit about visualization. This is my fourth topic. Visualization is really like where we can, if you look at it, Professor Ralph Peck, we always have to use eye. So visualization is kind of what you see is what you get. So that's what I want to show you a few things. So here again, I will touch base with some of the visualization work we are doing. I think, the visualization in geotechnical is very important. You can, we have seen some amazing pictures or visualization of a big mega city and what you have underneath the ground. And that will provide you where to go or if you have to put a tunnel, where you exactly have to really place it. So this is something we have been working. We also can do visualization in different ways. So the one project I will mention here is a dam. So one of the dams we have is the Tarrant Regional Water District. It's an old dam, so a lot of dams have these issues. So with the visualization, I can see where we may have an issue. So let me show you the one dam I'm going to talk about is an hydraulic fill dam. Just to give you an idea on hydraulic fill dam, the way the material is brought, then placed in a slurry, the coarse material settle first, then finer material will flow. So you have different ways of building the core. But a lot of times you don't get a nice homogeneous sections. You get high heterogeneity. And that is something, is common with hydraulic fill. So this is the dam where we have a nice project. One of the reasons we did this project is check on the seismic effects on the dam stability. So we don't have a lot of information on the construction records. It's the 1930s. So PB, Patterson Brinkoff, did some work. They did a lot of CPT work, which I'm also involved at that time. So we did have a lot of seismic cone penetration or piezo cone penetration along this. Paul Main will be very pleased to say, being a cone head, this is very important. I was able to convince both the PB and also the dam folks to do the limited amounts. Of course, with the proper plugging immediately, we were able to get good amount of data. So this is our typical CPTU data, and you can see you get your CPT properties, and then we did the Robertson method. So using the Robertson, you can get the soil behavior types. So you get all the soil behavior classification is given based on your tip and resistance. You correct it for pore pressures, and then you get the readings, you get the soil behavior. So we use this to characterize how the hydraulic fill dam is there, So one thing I can mention here, so these are along the crest, several CPTs. I'm just showing you the soil classification from the Robertson method. You see how much variability we have. We never have anything that's uniform along the whole, the crest of them. So one thing we did is we did a kriging analysis to come up with the 2D plots. So here we divide them into several groups because this is what it's supposed to be, 3 layers. So each of them is different. So 0 to 5 feet, you can see we try to do that normal distribution of the tip resistance. There's not a simple normal distribution. Same thing, 5 to 20, and then 20 to 50. There's a lot of variability. So we thought we need to really do kriging analysis and also stationarity analysis. So we did this. Again, one of the things we did is we went back and do the variogram analysis of all the entire CPTs. And then from the variogram, you can see the spatial variability. So we used geostatistics. Tejo did his work with this, and also Sayanthan, he did his PhD work also on this. So basically, we completely used the variogram to do the whole soil layering. So this is the 2D distribution. What you see is along the whole length of the dam. So this is the length of the dam, 0 to 2,000, 4,000 here. So you have several zones. So orange is your soil here, which is typically around clayey soils. You have some sandy soils at the top and also some sandy soils here. So when we did the characterization, when we showed these results we have a once every 2 months meeting or 3 months meeting. So they were very pleased because they're having some seepage issues around the zone 3, and then we found some sand layers there. So some of these layers actually explain why they have this information. So we built everything in ArcGIS platform. They have the whole thing. Then we did one step extra. We went with a 3D site characterization. So we used one of the software. So this is our 3D site characterization of the entire dam. We have LiDAR data of the dam, so we converted him into the whole thing. What you see is on both sides of the dam, and also the top dam, you can see it started playing. So everything what you see, the color-coded, is the soil type based on the soil classification. And then you see the core wall. It's some section you will see sheet pile walls. So you can see sheet piles here. So it will give you the entire distribution. You can see the sand material over here. Now you see. And you also see some of the borings. So this is the 3D geostatistics we use to come up with the visualization of the entire thing. So now they have this information. In the future, if they have an issue, they can go to the site, location, and slice it. They can get all the soil properties from CPTs, and then they can go and check the slope stability, different types of things. So this is one of the visualization nice things. We also did some induced seismicity effects and how the liquefaction for hypothetical scenarios. The dam is very stable. Basically, we did both Boulanger's method, Boulanger and Idris method, and also Robertson method. Again, what you see is some potential spots for a high earthquake scenario, which never happened in our region with the 0.3Z, but most of our earthquakes are very low. M3 is what we have. This was, again, Oklahoma has much more, but they're further away. So we did some ground motion spiking up to come up with it. Again, both the dam and levee were stable without any issues based on the seismicity we have seen. So again, this is a TRWD water district that maintains these dams. So we're able to do this work. So in the end, I'm going to unmanned aerial vehicles. This is done by one of my postdoc Congress. Again, we love playing with the toys. So that's our toy there. It's one of our, we actually get a lot of good information. This is a TechStart project. We are the first ones more than 2.5 years back to do this work on infrastructure asset management, to do these surveys and demonstrate how to be done. So we have worked with TechStart and TTI and also another Texas A&M Corpus Christi. They all have a UAV excellence centers. So we did a lot of work. So Congress did his PhD work on this topic. So first thing we did is where do we fly the drone? What are the things? How do we do it? Joe does a lot of great work with his center in Washington. So again, this is the part of the design. Like anytime you do the thing, you have to have a flight planning. You also have to have a FAA certified pilot, which happened to be my postdoc as a FAA certified pilot also. And then you need to have overlap because you are doing photogrammetry. You're taking images from different angles and then going into software and stitching it. So again, this is the flight path that shows. And again, we can do GNSS type system, which is very important because there's some areas that we have cloud coverage, we can work very well. So everything what we did on roads, embankments, bridges, around foundations for the bridges, we have collected a lot of data. I show you a few slides. Now I'm working with Naveed from LSU on these topics also. So one thing I can show you, this is one of our picture. What you see here is a pavement failed because of the bad subsoil. As you can see the cracking here. So this is the imaging from the UAV. This analysis is done on a software platform. What you see is a 3D imaging with complete visualization. You can cut this area. It'll give you what is the amount of settlement or rutting. So this information, by just flying, you don't have to go there. Flying along the road, collecting the data. Obviously, you can't fly over a live traffic. Do not fly your drones on top of a live traffic. But with the proper signage, you probably can do if the DOT gives permission. In our case, research DOT has given permission. So we're doing, and we're hoping to do more. So again, we can get a lot of information that tells you subsurface issues. And we also did some nice work near the Alpine, very close to the border. So this is one of the railway track, that we had to do the washouts. And again, one of the things we see is where the erosion took place, all the nice contours, we were able to fly. We can even build how much volume has the voids, if we can see that volume very clearly from the surface. If deep is not visible, obviously we can't do it, but we can tell how much of area grouting we may need to fill up this area. So the other thing we did is a rock cut. There was a presentation yesterday by Dr. Congress. So one of the things we did is for this railway, there's one railway section that is owned by this agency, is TxDOT is this particular one. It's not in practice, but they may use it in the future. So basically we were showing them, and then we went and looked at the rock cut slopes. So again, all you see is the imagery from your visualization of your data. So you can identify the areas where you have the steep sections, and then you can import this data into any software platform. We are working with a couple of softwares right now. And then if you know the properties of the rocks or the soils, whatever you have, you can go back and design it. Now I think you can do landslides also, so a lot of things. So this is, of course, a small height, but again, you can extend this to major things. So we're very fortunate with this study, and we are actually doing a lot more work. We have 4 projects on UAVs right now. Some of them are looking at transportation communication towers, and another one is the dams and embankments. And we're also looking at some slope issues with LSU. So there are a lot of interesting stuff. Hopefully we'll present it. Again, he did some analysis of the 3D slope stability. Again, it'll give you areas where the factor of safety is really critical. So you know the areas that need to be investigated further or maybe even repaired. And this is the NSF study, rapid study. We have recently started working on it. We are doing this data fusion. This came from taking the data from your drones and also Twitter feeds, so come up with a better way to know which infrastructure is really, because a lot of times you get false information. There's a dam breach. It's really not. The people may have to, in that hurricane time, they had to really go out. So we are looking at this study with the social background professor, and using technology data, and how do we come up with a better way to understand, so that we can provide the data quickly to Emergency Operations Center, so that can tell the public there's no issues, the bridge did not collapse, everything is okay. So that kind of information. So the drones can provide you visual data that really helps you. So again, I think more and more works you will see. I see a lot of interesting work. And we are hoping if Brad allows, we may fly drone in the next year conference in Dallas, provided we get a space to fly. So I just want to give you a summary. I live on expansive soil, I live in expansive soil, I live by expansive soil. I call them expensive soils. Really, that's the reason why we have a lot of issues and a lot of research. And a lot of my students really worked on several things. We did from basic research from NSF to applied research with highway agency or Army Corps or water district. We've been very fortunate. We have a lot of made some very good practical solutions that are implemented by different districts. Again, I think one thing I want to mention in the red font is what actually Professor Peck mentioned. It's very important for us to do the case studies. The case studies really help us in our understanding of these issues better. I mean, you can do lab, but sometimes in field, you apply, you may have sometimes some modification you needed. And so far in the expansive soils, we didn't have to do that much, but again, I can't say for sure because lots of times we probably 4 out of 5 times we are lucky. I think in geotech-wise, we are doing good. So the one thing I want to mention for our young faculty, particularly the new ones, the visualization construction 4.0. I'm very fortunate. I'm working with a group in France, École Polytechnique Lille. They do a lot of wonderful new work with 3D printing, UAVs, sensors, robotics. A lot of these things are related to either tunneling operations, are using sustainable materials for 3D printing, which is geotech. So a lot of these materials, in my opinion, geotechs can play a very important role. And I'm doing right now at A&M, actually doing some sustainable material, cheap clay. Take the clay and convert that into a flowable material that can be used for 3D printing. So you can build a nice home. Hopefully that is durable also. If you can demonstrate both, that's a very big incentive because it's cheap and it's inexpensive. You can do a lot of things very rapidly, particularly if it's a disaster time. You can build some small areas that can be using to house people. So that's an area where we actually see the construction 4.0 is really using technology. Alan Moore and a lot of these guys already doing wonderful work. In France, they have a lot of big construction industries, part of the university developing this work. So every summer they have workshops on 3D printing and see amazing things. And I'm hoping more and more. We already have several folks that are working in A&M, so the more and more you see. Geotechnical engineering, actually, we can come up with materials that can really help. So I just want to mention that digitization, automation, we are creating a new committee with the help of Board of Governors and our presidents. We may do an innovation committee to attract more of these industries. Sissy actually is involved with the board. She's the Board of Governors also. We are trying to create this. All we are looking at is virtual reality, or restore urban structures. You saw the visualization. You use AI, ML models. So all these things, I think, in my opinion, will be very exciting, and also hopefully will bring a new industry to this, this Congress. So that's something we hopefully will have more and more. And also, in our opinion, it can really attract a lot of young, engineers into our profession. So I think, there's a lot of, I would say, groundbreaking research there, exciting research that's going to come up. I see a lot of work here on the energy pile, so we are very, very fortunate. So I just want to say acknowledgements. I mean, my wife, Padma, and my kids, Anisha and Rishik, they really are the reason, because they know I spend a lot of times long weekends with my students, but they're very, very patient with me. Of course, my parents and my brother and sister. And I miss my Professor Ajad, Yalchin Ajad. He was my advisor. He passed away just a few months before I started my academic career in an unfortunate accident. Professor Tumai, even now I call him every month. He's about 80 plus. And again, I feel sometimes I'm half Turkish, because both my advisors are from Turkey. So, I have Ajad and Tumai, my thesis advisors. And again, I want to thank, again, my EDS award committee, starting with Tim Stark. Jim Collins wrote a nice letter. Sandy Houston, I hope you guys don't regret that he wrote those letters now. So I also want to mention Naveed Jafari and Tejo, Binod, and Chris Carpenter, who did this thing. It's really a surprise to me. I can't tell you how big a surprise it is. I also want to talk about some of my colleagues, particularly at UT Arlington. Professor Hoyos, unsaturated soils, wonderful person. Xinbao Yu, I work a lot with him now. Professor Qasim, he was one of my mentors. My current chair, Dr. Abul Mali, I work with him a lot also. And my new colleagues, but very esteemed colleagues also at A&M, starting with our president-elect, Professor Briat. Again, ever since I moved to College Station, he's wonderful. He was always giving me how to get things moving, and I'm very thankful to you, Jean-Louis. Really, really appreciate it. Also, Dallas Little, he's also worked with him quite a bit on sulfate soils. Robin, our chair. Marcella, I'm looking at a different aspect of expansive soil shrinkage, which we haven't done it. Bob Litton and others also. Again, UTEP, Professor Nazarin, I have and I showed you some of my textile projects. He's kind enough to include me as a collaborator on those projects. The best team. This is really my best team. And again, they surprised me last 3 months back. All these guys flew from different parts of the country and then came there. And again, all these guys, thanks Tom for giving the talk. These guys really, I think a lot of them are here. I just want to acknowledge you by standing up a little bit, guys. Don't be shy, just stand up a little bit. So really appreciate you guys. And they do all the great work. I just had the pleasure of coming and giving talks, So without them, I'm not there. I really think it's important to bring them to this, because my professor, Tumay and Ajar, used to take me to the geotechnical conferences, put that seed in my brain, and, I've been doing it, and I hope to do it in the long run, Again, I'm very thankful for everything. I get a little choked up at them. I'm so proud of also, both Laila and Reenu. They just graduated in December. Laila is working now in Seattle. I also want to say Ujjwal is at the University of Guam. Just want to say the other guys are working right now. And these guys here, Tejo, Srinu, and then Congress, and Sayantan, all these guys really, they put a lot of effort in this presentation. And Professor Briaz was telling me, Anand, you need to start working in December on this presentation. Thank you. I think I did that. I really started. Again, I really thankful to everything and thankful to the Board of Governors for giving this opportunity. Thank you very much. Thanks.
Thank you for a wonderful lecture.